Last time we already introduced the theory on group combustion, and I give you additional summary based on this page on our lecture slides 3.20. And Professor Chu proposed a model for group combustion in 1978. The definition for group combustion number basically is the ratio for the number density and separation distance between droplets. And here, n represents the total number of droplets in a given control volume, and S basically defines the non-dimensional separation distance between droplets in this control volume. And horizontal axis represent the variation on non-dimensional S, and the vertical axis represent how many numbers of droplets you have in this control volume. And you can see, based on the definition of the group combustion number, as you increase the number of the droplets or decreasing the separation distance between droplets, then you will make the G number, group combustion number, become bigger. Conversely, if you reduce the number of the droplets or increase the separation distance, then the G will become smaller. Large G represent you are talking about a group of so-called dense spreads, and the G number becomes smaller, then that means that you have a small number of droplets and also a larger separation distance for droplets in a given control volume. Then that relate to the dilute spread conditions. For dense spreads, okay, for example, if G number larger than 100, then you may have the spread frame described before as external shape combustion. External means you have a spread frame and surrounds the whole spread core. And the shape means those kinds of vapor coming out actually supported by the gasification of the outer layer of the droplets in the of the spread cloud. Okay, which means there is the outer layer just for evaporation, but in the interior of your spread core, actually you have so many droplets exist, but they do not have very efficient gasification. Then they cannot support fuel vapor from the center to the outer frame. And basically, the frame is only supported by the vapor gasified from the outer layer of the liquid cloud. But when you decrease the group combustion number, that means that you go to the a little bit dilute spread region. Since it is the less dense, then you will have a larger separation distance, and also you will not have too many. The number of the droplets reduce a little bit. In this sense, you can have more heat penetrate into the spray core to produce all droplets inside of the core to start to evaporate. Then they can support the fuel vapor coming out from the center portion to the outer surrounding. Then we call this as a so-called external group combustion. External group combustion means the spray frame still exists in the outer region of your spray core, but the support of fuel vapor coming from the whole droplets inside of the spray core. Okay, now the diffusion frame, the spray frame, stand at a certain distance away from the boundary of your spray core, and this means the external group combustion, and belong to the G number between 100 and low, maybe lower to the 1 or zero point 0.1 value. Okay, in these regions, and you may experience the external group combustion. And you further think about when you decrease the group combustion number further, lower than 10 to minus 2 to the order of 10 to minus 2, then you will figure out since the the spray coat become more dilute. That means that you have a smaller droplets exist in the spray coat, and the separation distance between droplets become large. And in this case, actually, the supply of fuel vapor coming from the spray cloud become weaker. And you have the feeling is that since the position of the outside outer spray frame basically supported by the fuel vapor supply from the spray coat. If the supply of fuel vapor become less, that means that your diffusion frame will move forward to the spray boundary. And in case if they cannot have a strong support to push your diffusion frame out of the spray coat, then this frame will penetrate and move into the interior of spray coat. When the diffusion frame move into the spray coat, you will find out as the passage of the diffusion frame moving into the interior of the spray coat, then the ignition of the single droplet may happen. Okay, then you will have a so-called internal group combustion. Internal group combustion means the group combustion occurs in the interior of the spray coat. That means that your diffusion frame sits in a certain position inside of your spray coat. Outside of the spray frame, outside of the back frame, actually you may have so many single droplet burning exist here, and the diffusion frame only supported by the small portion of droplets inside of your spray coat, and those fuel vapors supported gasified from this group of droplets support this small diffusion frame. That means we will have a back diffusion frame sit inside of your spray coat, just like the figure illustrates. Furthermore, you continue reducing the droplet number. That means that when you go to the downstream of your spray, since the gasification process already proceed for certain distance or certain time, some small droplet already gasified, disappear, and a large droplet becomes smaller, then the supply of fuel vapor will become less and less. Then the back diffusion frame will continuous move into the center part of your spray coat. Finally, they will disappear. All the droplets will be ignited and burned as a single droplet. Finally, you can go to the G number less than 0.01. Then you will find out in the field of in the spray field, actually you may all exist, or you may all have the single drop burning in the far downstream region. In this case, actually droplet the spray field is very dilute. Okay, the droplets actually they are separate with a large distance. Sometimes they are burning and sometimes they are evaporating. Actually, I already mentioned in our discussion on droplet combustion. In a sense, actually in this very downstream region, droplets may not have the envelope frame, but they will experience vaporization only because they exist in a very hot temperature environment. Then finally, you go further, then all the droplets will be evaporate, and they will go to the so-called turbulent brush frame. In that regions, you may think about is the turbulent premise frame, because all the fuel vapor mixed with the oxygen in the outer region and burn with the very just like a well-disturbed turbulent premise frame. And this is a very nice physical model to let you know how the burning for a spray cloud. Okay, and there is another description is more related to the to the full cone spray. That means that you do not have a very well atomizations. Then you may, when you do the spray atomization, then you may have a large droplets with large droplets with large number and exist in the spray coat. That means the evaporation process become weaker, and you may extend the whole the droplet appearance in a long actual distance. Okay, let's look at the other descriptions on the spray diffusion frame mechanism, and note this mechanism described by phase, and I try to give you the some understanding on those kinds of descriptions on the spray structure. Actually, those kinds of characteristics that just give you additional understanding on the spray characteristics under bonding condition, and they are just some kinds of extension from the understanding based on the group combustion. Okay, look at these spray structures. Can you look at the right-hand side? Actually, they describe the flow structure in different ways. The right-hand side give you some definition on the boundary. Here, there is a so-called cold core, right? Cold core means inside of the cold core temperature is low, and you have many large droplets exist in this core. That is simply you can think about is the so-called spray cloud. Spray cloud means that in this core, we has a lot of liquid droplets and has this gas phase, gas medians inside of the cloud. Okay, and you can identify this as the spray boundary here. Okay, spray boundary here. Definitely near the spray boundary, there is some fuel vapor coming out, and to meet with oxygens from the outside, then they will burn. Therefore, they identify the region for the chemical reaction. That is, the spray frame may exist in this region. The boundary identified here is the reaction zone. Okay, here they say, yeah, here this is a spray boundary. Spray boundary defined based on the smallest the droplet occurs. Okay, therefore you see if this is the spray boundary, actually they give you the understanding here the region between the spray boundary and the boundary of cocoa in this region. Yeah, as we referred to the previous group combustion structures, in this region, you may have some single droplet combustion, or you may have inner internal group combustion exists here. Okay, and the diffusion frame exists in these reaction zones. Okay, actually you can see the thickness of reaction zone extend further to the downstream sites. Okay, since in this region, in reaction zone region, you may have some droplet exist. Those kinds of droplet will extend the bonding zone when you go to the upstream the downstream site. Okay, and here there is a so-called jet boundary. Here they tell you there's some entrained gas, especially in the upstream side, because the pressure difference is larger in the upstream side. Then you may have entrainment from the outer air into the spray core. Okay, this is the typical structures for the flow structure for the two-phase spray burning. And the left-hand side give you some understanding between the interaction of the liquid droplet and the gas phase, gas medium. Initially, when you look at the upstream side here, there is figures to represent the differences between droplet velocity and the gas velocity. Initially, near the injection port, the droplet has a larger velocity compared with the gas velocity. Okay, but when you go to the downstreams, since the liquid droplet will transfer their momentum to the gas phase, and the gas phase, the gas medium will be accelerated by the burning temperature, because temperature high, then the gas medium will be accelerated. Therefore, to the downstreams, the difference between the gas velocity and the droplet velocity will become smaller. Okay, in the downstream region, this is tell you there is a very strong momentum transfer between liquid droplet and the gas medium. And if you look at the concentration distribution and also temperature distribution based on the spray frame consideration, you can see in the middle part here, and I already mentioned here, there is some fuel vapor supply from the interior of the spray core, then the fuel vapor coming out. And here at the center, you can see you will have a highest fuel concentrations, but those fuel vapor concentration will decrease to the almost diminished at the reaction zones, because there some oxygen diffuse in to burn with the fuel vapor. Then your spray fan will sit around here, and when you finish the chemical reaction, all the heat of combustion release, then you can have the maximum flame temperature just coincide with the location of your diffusion flame. Also, the locations for the minima fuel concentration and oxygen concentration positions. Okay, and then here you can see there's still have some droplet size, right? And in the center region, there's a big droplet, and at the diffusion flame, the droplet is smaller, but some droplet exist in the outer region of your spray flame. Okay, and that means that actually we're looking at the chemical reaction zone. Actually, is the border. The main diffusion flame is a narrow occur at the positions of the maximum temperature, but they still have some tiny droplet burning outside of the diffusion flame. And this characteristic will extend to further downstream. You will find out they still have a maximum temperature distribution, but they do not have a big the high top mountain change, and the temperature distribution become more uniform in downstream, because in this region basically belong to the so-called turbulent premise burning. They have an oil mix of the fuel vapor and oxygens, and you cannot have very distinct behavior on the diffusion flame structures. And you can see you may not have a droplet exist in the outer region of your diffusion flame. And this, if you look at the flame structure or flow structure from the upstream side to the downstream side, you will find out the liquid behavior become less important, because they go through the gasification process, and they becomes a vapor, or they burn with oxygens to produce the products. And this is an overall pictures for you to look at this schematic representation of coaxial spray diffusion flame. Is more related to the full cone spray. Okay. Now there is some comments that one by one I just read through it and try to mention their comments. The first one, they say the spray leaving the injector is highly non-uniform, with a small droplet at the periphery and a larger droplet near the center line. Yeah, this is a typical spray characteristics for a full cone spray. Okay. And initially, in the upstream side, definitely you have a larger droplet size distribution in the vicinity of injector. And later, when you go to the downstream side, the droplet size will become smaller. Okay. And the second comment, they mentioned the velocity difference between the droplet and the gas is largest near the upstream zone, but those difference become smaller because there is a very strong momentum transfer between liquid droplet and also the gas medium. Okay. And typically, this plot is additional to give you the understanding on the region for spray flame. Here they tell you the inner cone. This is a core of a core higher velocity droplets, and the droplet has some acceleration zones here, accelerated by small droplet accelerated by the half product. Okay, and the air entram to the spray flame. And they tell you actually there is a so-called primary reaction zone is a thicker compared with the gaseous diffusion flame. Okay, and the spray boundary exists and denoted by the broken line. Actually, the spray boundary means in the outer region of the spray. Actually, they still have some tiny droplet exist, and they will gasify and burn in these regions. Okay. And the third comment, Yeah, this pictures I took from the Scale and McCreen in 1974, additionally to help you to understanding the definition for the spray diffusion frame, because in this sense, if you compare with the gaseous diffusion frame, actually the frame thickness, I mean the high temperature thickness, is a relative burden for the spray frame, since in the spray field you may have some small tiny droplets exist in the outer region of your bulk diffusion frame. The the third comment from phase, they say small droplets around the periphery of the spray evaporate to provide few vapor, which is consumed near the outer portion of turbulent diffusion frame. Okay, but large droplet, however, they can travel through a considerable distance before evaporation and a combustion begin. It is due to the relative high inertia of larger droplet. Definitely, the lifetime of a larger droplet is longer, then the momentum of large droplet can push your droplet to move further to the downstream. They can survive, but anyway, they will finally gasify completely as a fuel vapor or burn out completely in the downstream side. The fifth comment here, they say the disappearance of droplets is closely correlated with the position of maximum temperature in both radial and axial direction, which means that actually those droplets almost complete their gasification very close to the diffusion frame. Okay, and the sixth comment, the bulk of fuel evaporation occurs in relative cold, low oxygen concentration region. That means this belongs to maybe close to the external shape of group combustion, and maybe the external group combustion model described by Professor Chu. Poor atomization is conjunction with large gas velocity years region where evaporation of large droplet occurs in an oxidizer environment. This is a final comment to let you understand if you have a poor atomization means the droplet size in certain regions is too big. Okay, and those large droplets will continuously exist and in certain conditions without additional small droplet support, they will evaporate or burn by individual diffusion frame supported by the oxygen in the environment. Okay. Now, the comments up to here, actually, we try to give you some understanding for the spray structures and also the spray diffusion frame structures. But many people try to think about, since for spray frame, it is very difficult to do the measurement or to do the predictions. Now, I try to give you some experimental results to tell you how to simulate a spray diffusion frame. Therefore, here we try to give you some understanding about the modeling on the spray diffusion frame. Here they say in some cases, spray combustion can be modeled by ignoring the details of spray evaporation and treating the system in the same manner as the gaseous diffusion frame. And in many circumstances, such simplifications are unwanted, and the turbulent two-phase flow must be considered. Actually, here they give you the two important comments. The first one, later on, I will give you some experimental judgment. If you consider a well-atomized spread, that means that you can provide a bunch of small, tiny spray, a tiny liquid droplet in your spray field. In this case, actually the evaporation is very strong. The gasification will be complete in a short distance. Okay, in the axial direction or the radial direction, either way. Then that means that it's easier to have a very efficient mixing of oxygen with fuel vapor, then the bonding is very similar to the gaseous diffusion flame. In such case, then you can use the gaseous diffusion flame to simulate the spray flame you may have based on the well-atomized sprays. But if you consider, especially for the full cone sprays, okay, the solid cone sprays, that means the atomization is not too good, then you may have some big droplets. Then you need to think about the evolution of these larger droplets in the spray field, because they will extend their droplet lifetime longer, exist in the far downstream side, and they just do the individual droplet bonding. Now you need to think about the turbulent two-phase flow. Okay, these are the two major comments. Now I try to bring the first some observation from the experiment results to look at the first comments. Can we use the gaseous diffusion flame to simulate the spray diffusion flame? Okay, this is the first part I want to explain. And those experiment results taken from the Onuma and Ogasawara published in 1974. And there is another paper published in 1976 with the same group. And they give us a very deep understanding on well-atomized spray diffusion flame. Okay, here they consider the spray combustion flames of actual jet or kerosene under low turbulence conditions by using air brush atomizer. When you look at it, the title basically they tell you the well-atomized spray condition controlled by the first one, the air brush atomizer. Air brush means you have the external mixing and the internal mixing, right? You use a large amount of air to produce well-atomized spray. Okay, this is the one condition. The second condition is they use the fuel, they use a kerosene. Kerosene has the lower boiling point, which means they can be easier to be gasified in a hot temperature environment, which means the liquid droplet of gasoline can easily to be gasified and to produce a fuel vapor to support the spray flame burn as the gaseous diffusion flame. Okay, now let's look at the first figures. Okay, and they use there is some comparisons. The first one in this figure, they use a kerosene as this is a liquid spray, right? They look at the characteristic of the kerosene spray flame, and the lower figures they try to bring another friends, and this is the propane diffusion flame. Propane is a gaseous fuel, right? And they try to give you the some comparison on the burning characteristic between the kerosene spray flame in the upper figure and propane gaseous diffusion flame in the lower plot. Okay. Now try to figure out the flame structures for the kerosene spray. Here, the first one, no, I need to say that the coordinate system is for the horizontal. They just give you the understanding. The measurement will follow from the exit of your injectors, 0, and go to the downstream up to 60 centimeter. And in the horizontal axis, they have a different scales for different properties they measure. Okay, now I try to make you some understanding on individual variation of the data measure. The first one, there's n here. This is a solid circle, right? Symbol. Here, n represent a number of your kerosene. Okay, and you can see near the injector port. Actually, there is two dense. You may not have two more exact results, but here, starting from around maybe 18 centimeter, you have a data. There is a number. Here they can find out measure. The number is around 10 to 12. Okay, densities, and they will continuously reduce and diminish around 25 centimeter. Okay, and this tell you the existence of your liquid droplets. Okay, And look at the propane here. They measure the concentration of propane. Here you can see very close to the injector port, they have a high concentration of propane, but the concentration of propane reduced around the actual distance and disappear a little bit longer, about 35, extend to the a little bit downstream compared with the lead for the kerosene. Okay. But anyway, you find out there is the disappear of the number of kerosene, but they may give you the understanding they still have some vapor coming out because droplet size disappear, all transfer to fuel vapor, right? And those fuel vapors start to have some a mixing with oxygen, and they start to have some decomposition to the intermediate species. You can see there is a HC radical occurs, CO radical occurs, along with the decrease of the number of the droplets. In a similar way for the propane fuel, when you look at the decrease of propane concentration, follow that you can see the HC concentration, carbon monoxide concentration will increase to a maximum value, then disappear. Those decrease of the CO and the HC represents the further recombination for the products occurs. Then you can see carbon dioxide increase later on, okay, and at the same time temperature increase to a maximum value, okay. Then you can see this is a clearly tell you the combustion structures for the propane, and you can figure out those kinds of behavior occurs similarly in the kerosene spray flame. Then look at the sequence for the burning process. Initially, you have some liquid droplets, but they start to gasify. Then the number of the droplets becomes smaller. Then finally, all the vapor gasified becomes a fuel vapor mixed well with oxygen. They start to have decomposition to produce some intermediate species. For example, HC and the CO, they reach to a certain large value. Then they will go to the final recombination reaction to produce the carbon dioxide. At the same time, heat of combustion release, then they will reach to the certain high temperature point. Later on, they will reduce because they go through the downstream side. They have some mixing with the cold gas environment. The temperature decrease. Okay, in this the process from the upstream side to the downstream side, you can see the oxygen initially is higher, okay, because at the center region you have some entrainment of air into your spray core, but they will move to the minimum value because some oxygen some oxygen consumed for the chemical reaction, and later on they will increase again to reach the same conditions in the environment. Okay, and similar way you can see the oxygen variation is very similar in the gaseous propane flame. Based on these two figures, then you can figure out under the burning for the spray or for the propane, for the kerosene spray, and for the propane gaseous flames, they have a similar variation on gaseous concentration and fuel conditions, and also the temperature. They are almost the same. Okay. Then they give you the conclusion is that the turbulent gaseous diffusion was analyzed by using the same apparatus and changing only the fuel from the liquid kerosene to gaseous propane, which means they use the similar apparatus, and they find out the spray diffusion flame was found to be very similar to the turbulent gas diffusion flame in structure. Okay, this is a very important conclusion from their experiment. And especially I need to emphasize in the experiments, and they use wear atomizer, air brush atomizer, and they use the low boiling point liquid fuel kerosene, then they have this nice and good comparison between the spray, the kerosene spray frame and propane gaseous diffusion frame. And the same group did a further experiment and published it in 1976, more focused on the NUX formation structures. Okay, and they tried to look at the variation on NUX concentrations. And the first one, they present the NUX concentration variations in different way for a kerosene spray frame. These two figures actually coming from the kerosene spray frame. The left-hand side, they just give you some reminder on the concentration, gaseous phase concentration and the temperature, and also the droplet numbers from previous experiments, but they give additional nice for NUX formations, NUX concentrations along the actual coordinates along the center line. Okay, and along the right hand side, they measure those kinds of properties along the radial direction at a certain positions away from the injection port, and the position is around x equal to 20 centimeter, the actual coordinates. Okay, now let's look at the NO formation here. That where is the line for the NO formation here? Okay, this is the inverse triangle symbol. Okay, here you can see invert triangle symbol tell you initially near the injection port, actually the NUX is very small. I need to mention here, basically for this study, because we use the kerosene do not have any nitrogen content in the fuel. That means that all the NUX formation coming from the so-called thermal NUX formation. Thermal NUX means in the combustion process, because we are burning those fuel in the air environment, and when you have a very high temperatures, and those kinds of nitrogen coming from the air, they will absorb heat for the thermal decomposition to release the nitrogen atom, and the nitrogen atom has a possibility to recombine with the oxygen atom in the combustion process. Then they will produce a so-called NUX. Okay, and those NUX formation is strongly influenced by the temperature. They require absorb a certain amount of heat. As I mentioned earlier, the threshold temperature for thermal NUX formation is around 2000 K. Okay. Then you can see here there is a very small NUX concentration near the injector port, but increase continuously follow with the temperature. Okay, you can see temperature increase, then the NUX increased, and they shift a little bit in the downstream of the maximum temperature and reach to the maximum points, and later on they decrease. Actually, these kinds of variation on NUX formation is controlled by the temperature variation. Is completely similar to those described for the gaseous diffusion frame. Now go to the concentration distribution along the cross section of the spray jet. Then you can see here there is NUX here. You can see there is a two peak occur. Okay, then in the left hand side there is a peak for NUX formation. The right hand side there is also a two peak, another peak exists. And those kinds of two peak behavior is exactly the same with the two peak for the temperature profile. The two peak for the temperature profile means there is the two frame boundary to identify the nature of your diffusion frame. Okay, and those positions for the peak of the temperature and peak of NUX almost occur at the same positions. Okay, this is another evidence to confirm the M4 formation is very for the spray frame, for the kerosene spray frame is very similar to those described by the gaseous diffusion frame. Okay, then they do the measurement for NOx concentration for different actual distance. You can see X equal to 10, 20, 30 Fahrenheit to 50. You can see in the region of the spray diffusion frame, since you still have a bulk diffusion frame surrounds all the spray cone, then you will have the nature for the maximum temperature and the maximum NOx concentration exists in the boundary of your spray frame. And that means that you will always have a two peak, okay? Unless you go to the very far downstream, 50 centimeter, because now you move to the region with the well mix of oxygen and the fuel, then there is the turbulent brush frame. You will not have a very distinct diffusion frame boundary. Then the whole NOx distribution will more like the some kinds of gaseous concentration distribution for given gaseous jet. Okay. And they try to pick one of, for example, is x equal to 20 centimeter. Pick this NOx distribution curve, and they estimate the equilibrium ratios at these conditions. And you can figure out here the occurrence of the maximum NOx concentration is very close to the equilibrium ratio equal to 1, okay, for both sides. And this confirms that because the thermal NOx is actually controlled by the temperature, okay, where is the maximum temperature? Actually, is near the position of diffusion frame, right? And at that position, we always think about the fuel diffuse at this position, just complete consume with oxygen and burn as a stoichiometric. Okay, this is a very nice experimental observation to confirm the NO NOx, the NOx, the NO formation is completely be described by using the gaseous diffusion frame. Therefore, they give a conclusion here. They say in the combustion of an actual kerosene spray, NO concentration peaks were found in the outer part of the frame, and there they were located approximately at the points where the gaseous temperature is maximum and the local equilibrium ratio is unity. Okay, and this kinds of condition actually is it can be confirmed by looking at those situations for gaseous diffusion frame. And this tendency is the same as that reported by turbulent gaseous diffusion frame. And these two experimental results is very nicely to give you the idea to how to describe the spray frame structures as you are looking at the well atomized spread. And from the experiment result, they suggest that you can bend the gaseous diffusion frame to model the frame length and the frame thickness you may have for spray diffusion frame.